partially thanks to Dr. Magalotti. Our transportation program is healthy again. And this time we have 5 healthy transportation students who conned one construction management student into joining their team. Anybody who drives around Oakland knows where Bates Street is. Okay. Continual backup. For a long time, lots of people have said something should be done about it. There have been plans to improve it. And this group has decided they would study the problem and make a recommendation. Those of you who heard the first presentation, I think I said something about real world. That's our theme for today, real world. And if you want to think about the real world, think about these guys out in the rain with their clipboards. There goes a Volvo. There goes a Ford 150. That's the real world. We're looking forward to hearing this presentation. I didn't get to hear it. That's right. You offered me the opportunity, and so I think I'll just sit back and chuckle. Amy Hummel is the team leader.
Great. Good morning, everyone. We'd like to start off by thanking you for coming to our presentation. My name is Amy, and this is our team, Eric, Nick, Chris, Pete, and Matt. And together we are No Delays Engineering, working to pave the way to a better future. Our team has created a preliminary plan to upgrade Bates Street here in Oakland by adding 2 lanes and reconstructing the existing lanes. Through this presentation, we will provide you with a traffic design study, a model of the existing and proposed conditions, a preliminary roadway and pavement design, and a schedule, phasing plan, and estimate. Now I'll pass it to Chris for some historical information.
So I just wanted to go into a little bit of detail about our project location. So as Amy said, we'll be looking at the Bates Street corridor, particularly the region between 2nd Avenue and the Boulevard of the Allies. This particular roadway functions as the gateway to Oakland, as the main access point to major universities such as the University of Pittsburgh and Carnegie Mellon, as well as a large employer in UPMC and the rest of the Oakland Business District. And this makes this corridor an important corridor for the overall functionality of our regional transportation network. So I'm going to go into a little detail about the project goals. No Delays will work to cost effectively relieve congestion along our corridor while simultaneously addressing queuing issues and attempting to improve overall safety and comfort for the drivers. No Delays is also working to have this project bring Oakland in more so in line with the current 2025 Oakland Master Plan. And also we're aiming to create a more aesthetically pleasing roadway that accommodates and encourages multimodal usage. So I wanted to go into a little bit about the history of Bates Street. So you can see here on the left we have some pictures, some perspectives of Bates Street from 1911. And on the right we have some perspectives on how Bates Street currently stands today. And as you guys can see, there's been minimal changes to the overall geometry of our roadway, even though the 1911 roadway was designed with horse-drawn carriages in mind. Some other problems that we have is structures built right up to the edge of the roadway that kind of limits expansion of the roadway. And while Pittsburgh has modernized and expanded a lot in our transportation, this particular corridor seems to be overall lagging behind. And it's evident that this roadway was built without thinking about future considerations. And you can see that in this next picture. You see the Hot Meadow Street Bridge has been completed. It's now a roadway structure. We have the J&L Steel Mill, which is now removed and now is home to Technology Drive and the Pittsburgh Technology Park. You can see 376 in At this time, it ended actually at Bates Street, and so we have completed 376, and while all this expansion and modernization has happened, Bates Street seems to be overall lagging behind. So I want to talk about our existing roadway. In our existing roadway, we have 2 lanes, 2 basic travel lanes. They're approximately 1,700 feet in length. We have a couple of off-ramps from I-376 that come into our corridor. These are both existing stop-controlled intersections. We have 1 on-ramp to I-376, which does not have any control on it, and 2 signalized intersections at either end of our corridor, one at the bottom of the hill with Bates Street and 2nd Avenue, and a signal also at the top of the hill with Bates Street and the Boulevard of the Allies. And just to give everybody kind of an idea of the traffic volumes that we're dealing with, we wanted to put a couple comparisons up here, and you can see that Bates Street exceeds the annual or the average daily traffic of both Forbes and 5th Avenue. And with that, I'll pass it to Nick to talk about our data collection process.
So the first step in our process was data collection. We used electronic count boards provided by Dr. Magalotti to go out on Wednesday, September 21st and count cars. This process involved sitting at various intersections and literally observing the cars as they made their movements. In our case, we had to sit at the top of the hill at the Boulevard and at the bottom of the hill at 2nd. And then I counted at the end of the Oakland exit at 376 near the first building going up northbound. So I counted the movements at the group at the top counted all movements at the Boulevard intersection. The group at the bottom counted all movements at the 2nd intersection, and I counted the movements at the 376 ramps, the 2 off ramps, Oakland, Glenwood, and Hodge Street, the little street that winds around behind the buildings on the southbound side. So we went out there during the Oakland AM and PM peak periods, which are 7 to 9 a.m. and 3 to 6 p.m., which are different than normal standard peak hours, which are 7 to 9 a.m. and 4 to 6 p.m. By doing the counts during these peak hours, we could determine the worst case scenario, or the peak interval, which leads to our peak hour volume, or the hour in which we observe the most amount of cars. So we took our count boards back, uploaded our data, and organized it into an Excel file. And what we came up with was a table similar to this, though this is really only a portion of it. As you can see in the leftmost column, the timings are broken up into 15-minute intervals. These intervals are part of the options available on the count board, 15 being the most standard interval. In turn, we can be more flexible in determining our peak hour volume versus just having counts per hour. That being said, we determined our AM and PM peak hours to be 7 to 8 a.m. and 3:15 to 4:15 p.m. Now, with the peak hour determined, there were some adjustment factors that needed to be considered. For example, the Greenfield Bridge and the Liberty Bridge were both closed at the time of our study. This potentially led to an increase in cars traveling Bates. However, after consulting a previous traffic study, we concluded that the counts were similar and that the bridge closures did not have much of an effect on our counts. Additionally, we applied queuing and growth projection factors to the counts, which I'll describe over the next couple of slides. These factors helped us be conservative in our estimation of the cars. So I can't talk about those factors before first talking about network balancing. The picture on the right is a snapshot of the entire road network, the top being the Boulevard, the bottom being 2nd Avenue. Both of those intersections are blown up on the left side of the screen. So as you can see at the intersections, the turning movements from our peak hour from the table in the previous slide are listed according to the movement made, the AM being the first number and the PM in the parentheses. So now the idea of network balancing is that every car that goes into the system must come out of the system, or conservation of vehicles, if you will. In other words, every car that enters at the top of Bates must exit somewhere within the system, such as Hodge Street, 376, or 2nd Avenue. So the way this is done, for example, is by tracking the amount of cars entering the system at the top of Bates, then adding or subtracting cars as they enter or leave the system. For example, adding cars on reaching the Glenwood exit because those cars are entering the network. What we're left with are a certain amount of cars entering 2nd Avenue. The cars counted, and the cars networked from the top are compared and adjusted as needed. The same process was done traveling northbound on Bates from 2nd Avenue to Boulevard. The reason this process is done is because no one's really perfect. No matter how easy it seems to count cars, the reality is that some cars can be missed. One way or another through network balancing, we can make sure that each car was accounted for. Now, with the idea of network balancing in mind, we can go back to the adjustment factors. The first one I'll address is the queuing issue. Basically, this problem arises from the observation that there were quite a few cars that were not able to enter the system as each 15-minute interval ended. We knew this because there was a beep at the end of each 15-minute interval. So to account for the cars that were left behind, we took measurements to determine how long each queue was. As you can see in the picture, we measured a 450-foot queue for the cars that wanted to turn right onto Bates going southbound from the boulevard. Similar distances were observed for cars going southbound on Bates from Pitt's campus and for cars going northbound approaching the intersection from the boulevard. Next, what we did was take the standard distance of a car, which is 25 feet, and divide that number into the observed queue length. The number that results is the number of cars that wanted to enter the system during the particular 15-minute period but could not actually enter. So for example, dividing 450 feet of the observed queue by 25 feet, we get 18 cars. Now that number is multiplied by 4 to account for the total cars that missed the interval during the peak hour. So in this case, the total cars that needed to be added to the southbound system from this movement was 18 times 4, or 72 cars. The same process was done for the southbound Bates movement at the boulevard and northbound Bates movement at the boulevard. So as you can see in the pictures on the screen, the counted number of cars were modified for the amount of queue cars that should have entered the system, 152 cars being added to the southbound direction and 80 cars being added to the northbound direction. Then the network was balanced all the way down. Then the network balancing came back into play. We balanced the new numbers down the system all the way to 2nd Avenue to again account for every car. This time the northbound lane was balanced in reverse from the new numbers at the boulevard to calculate the queue that should have entered the system from 2nd Avenue. Again, this helped to be conservative when we modeled the existing conditions. One thing to note is that we proportioned the cars out as they went down the system. So in addition to the queue lengths, we took a growth rate into account to help predict the amount of cars that would be traveling the corridor daily as if the road existed 25 years in the future. We applied a 1.6 annual traffic growth rate, which came from the Southwest Planning Commission, to our numbers, and it left us with the model shown on the right, our absolute worst case scenario. So now with our existing AM and PM counts plus our future counts, we could model Bates.
So to get into a little about the modeling, we used a program called Synchro 9. It's a traffic analyzing and simulating program. So like Nick had just said, we inputted the existing traffic volumes into our Synchro model and created the network, put the volumes in, ran the model. We discovered levels of service at the intersections. Levels of service are based on seconds of delay. We'll get into a little bit of that later. We also took the 25-year projected volumes and put those into another model to then figure out, to play around with, so how we could see how we want to design our road for the future. We also reached out to the city of Pittsburgh to obtain the signal timings for the intersections so we could accurately tell the level of service. So some of our goals for the modeling is in an urban area, you design to a level of service D or better. And as you can see in the table, that's a delay of anywhere between 35 and 55 seconds on average at the intersection. This was used with our 25-year projected volumes, and our main goal was to eliminate the excessive queuing. So as you can see, here's a model of our network, both existing and proposed. You can see right now that the level of service at the boulevard is a level of service E. This is for the AM peak, which was worse than the PM peak. So then with our modifications, after changing some lane configurations and adjusting the signal timing, as you can see on the picture on the right, we brought the level of service up to a D. But as you can tell from the drawing, we had to add a couple lanes on the northbound side outside of the other proposed lanes. So like I said, we changed the signal timings a little bit just to try to improve the intersection level of service. As you can see existing, there is more time going to the boulevard because that is, as of right now, the major road. We're proposing to add more time to the Bates Street phases to allow for more of those cars to clear. To get into the other intersection at the bottom of Bates Street at 2nd Avenue. Because of the bridge For the trail and 376, we couldn't really modify anything on Bates Street. So we played with the signal timings again. As you can see, the level of service existing was F. We brought it up to a D. We had to do a little bit of minor modifications to 2nd Avenue. So we are suggesting that within the next 25 years, 2nd Avenue get widened 1 lane on each approach. So as you can see, here we're just adding another lane, and here we're adding an exclusive lane. With those lanes being added, we bring the level of service of the intersection as a whole to a D. Again, like I said, we changed the timings a little bit. Now there's 2 different timings because the traffic on 2nd Avenue is very directional. In the morning, everything goes downtown, and in the afternoon, everyone's leaving downtown. So that's why you can see that the timing is a little different for both the AM and PM. It's pretty similar to the proposed. But that was just to maintain, like I said, the level of service D that we need to achieve for an urban area. So like I said, Synchro 9 also runs a simulation software called SimTraffic. So we have a little video here to show you the existing conditions of Bates Street. Our main concern is the Glenwood exit. Right there you can see 1 car went through, but that's about it. After that, everything backs up, and the queue from 2nd Avenue extends all the way past the Glenwood exit. That causes the backup on the off-ramp, and the backup gets so bad sometimes that cars end up sitting on 376 stationary in travel lanes and have nowhere to go, which is a very hazardous safety issue. So that's just a little model of that. And then to show how we improved it. So with our adding of 1 lane on each side, or with adding another lane in each direction, you can now see that the queuing doesn't reach all the way back to the Glenwood exit, thus allowing more of those cars to freely flow and not back up onto the parkway as excessively or at all. Pass it off to Chris.
So I wanted to go into a little more detail about our design goals. So from that model that was just shown, we knew that we had to increase the capacity of our roadway from 2 basic travel lanes to 4 basic travel lanes. And this expands actually up to 6 lanes wide at the intersection with the Boulevard of the Allies. And while we're doing this, we also wanted to provide an intersection redesign at Bates Street and the Boulevard of the Allies. Throughout this whole process, we wanted to also keep in mind driver and pedestrian cyclist accessibility to Oakland and safety. And as with all projects, cost is a main driving factor. So we wanted to make our design be able to minimize the land acquisition and demolition that would be required for the completion of our project. So some of our guidance materials that we chose to use, we chose to use the PennDOT publication, Highway Design Publication 13, and also the AASHTO Green Book, which is the geometric design of highways and streets. So using those materials, we were able to do the first step in design, which is the roadway classification. We selected to classify our roadway as an urban principal arterial. The definition of a principal arterial is a roadway that serves major centers of activity and also carries a large portion of area travel, even though the road itself constitutes a small portion of the total roadway network. So getting into our actual roadway design process, from that model it gave us the recommendations that helped us govern our overall design. And in place of survey data or existing plans for our roadway, we had to generate a surface. We had to download some 2-foot contour data from the Pennsylvania Spatial Data Access website. And this allows us to have a 3-dimensional representation of our existing ground layer on which we can accurately build our roadway. So we chose to use AutoCAD Civil 3D as our software for design. And whenever you're designing a roadway, there's 3 main components. You have first your alignment, which is your center line of the roadway, and it's your horizontal geometry of your roadway. And here you can manipulate design criteria such as minimum radius of curvature and also horizontal stopping sight distance considerations can be taken into account here. Secondly, you have your profile of your roadway, which is your overall vertical geometry. There's not really too much to say here because we're recommending that they just match the existing conditions of the roadway. And last, you have to produce typical sections for each different segment of your roadway. So one problem that we ran into when selecting some of our design criteria was with our design speed of 35 miles per hour. This led us to a large minimum radius of curvature of 510 feet. This made it difficult for us to fit our roadway into the existing terrain without severe modifications. The length of our roadway is also relatively short, so we had some safety concerns, and we had additional safety concerns with the grade of the road being a 9% grade. It's a rather steep grade, especially for an urban setting, so we had safety concerns and vertical sight distance concerns with that design speed. Higher design speed also promotes higher operating speeds, and a design speed of 30 miles per hour instead of 35 miles per hour also allows us to use no super elevation in our roadway, which made overall roadway design a little more simple for us. So ultimately, we selected 30 miles per hour for our design speed. Some of our other governing design criteria, as I said before, we have our design speed of 30 miles an hour, which means our posted speed will be 25 miles per hour. We selected the design vehicle of the WB40. Our horizontal stopping sight distance calculations came out to about 220 feet, and our minimum radius of curvature, it was previously 510 feet, and we got it down to about 330 feet. We'll go with a normal crown roadway. It's a 2% cross slope. Any horizontal sight offset, sight offset should be at least 5 feet off the shoulder of the roadway, and as previously mentioned, for our profile, we'll be matching the existing grade, which varies between 3 and 9%. And with that, I'll pass it off to Pete for our complete roadway design.
So like Chris said, we were able to use Civil 3D to create our corridor. This is a visual of Bate Street, Boulevard of the Allies, Hodge Street, the Glenwood exit off-ramp, and the Oakland exit off-ramp. I just want to mention that the double yellow line that runs through Bay Street, it would be our center line alignment. I also break this visual up into 3 sections so we can kind of get a feel for the design elements for Bay Street. So this visual shows the section of road located between the Glenwood exit off-ramp and Hodge Street. The major problem with the Glenwood exit off-ramp is the backing up on the I-376. So we added an additional lane for capacity. We also made the Oakland exit off-ramp its own lane, so that would not back up as well. You see there's orange hashing, which represents the wall offset that goes from the Oakland exit ramp up to the Boulevard of the Allies. Also, we have the Fraser Street stairs, which come down from Fraser Street onto Bate Street, and we will be talking about those later in this presentation. So this figure shows the existing and proposed typicals for the section of roadway previously shown. These figures show the lane configurations. Our proposed typical introduces a 12-foot bike ped path as well as a 4-foot buffer zone. The buffer zone was designed to keep a greater distance from vehicles and cyclists as well as pedestrians. The buffer zone also acts as a kind of a green zone. We want to plant trees or grass in that area. Like I said before, the major change in this section of road is adding the southbound lane to improve capacity. So this section of road shows Bate Street just above the Glenwood exit off-ramp, and it goes to the Boulevard approach. In this proposed typical, we continue with the bike ped path as well as the buffer zone. Here we introduced 2 additional travel lanes, one to both the northbound and southbound side. Okay, this is the last section of our street. This is leading up to the Boulevard of the Allies. The proposed typical in this section of the road differs most dramatically from the existing. Here we add 3 additional lanes to the 3 lanes that are already there. We add 1 travel lane to the southbound direction and 1 left turning lane and 1 through lane to the northbound side. So a major reason why we wanted to implement a bike ped path was safety, of course. We wanted to separate vehicles and cyclists the best we could. The bike ped path would provide easier access to Oakland as well as downtown Pittsburgh. So you can see in the picture, that's the intersection of 2nd Avenue and Bates, and the red arrow actually marks to the Eliza Furnace Trail, which goes downtown to downtown Pittsburgh as well as South Side. So we really wanted to use that. We wanted to get a bike ped path down there for access. I'll hand it off to Eric to talk about traffic signal design.
So to go more in detail about the intersection at the Boulevard and Bates, like Pete said, we added 2 additional lanes on top of the lane that were already there on the northbound direction. We have 2 exclusive left turn lanes. That was necessary in order to accommodate the volumes. The left turn volumes are almost equal to the through volumes, so they're pretty high. We have a signal head facing each approach for clarity. As you can it's kind of hard to see on this because of the crosswalk, but we actually have a second set of 4 signals for the northbound approach, and that's to allow vehicles that are coming up the hill, just give them more advanced warning as to what how the signal is, what phase the signal's in right now. Also, we are proposing, if you can see up here, to add a second lane on the northbound side of the boulevard. To do that, currently that is parking. We propose that the parking be removed up to McKee, and those 2 lanes be carried all the way to McKee, and then the left lane become a left only to then turn onto McKee. We felt that with our design speed being what it is and the intersection being as wide as it is, the offset that you see for the through lanes, there shouldn't be any issues there. So like I said, phasing a lot. So to get into the way this traffic signal is going to operate, there's going to be a protected, prohibited left turn phase for the northbound approach. So that means those left turns are going to have exclusive green arrows to make that movement, and then they will go red and stop. Currently, the left turns are protected, permitted. Therefore, they get the arrow first, and then it just goes to a green ball to allow movements where there's gaps. So that would be the first phase. That and the rest of the northbound movements with a concurrent, because we channelized the right turns down to from the boulevard onto Bates. That just becomes an overlap with a yield. It's just a channelized right turn, which makes it nice and easy for the boulevard to clear that queue that we were having troubles with currently. So after that, after the protected lefts would stop, then southbound Bates would then continue, keep going, as you can see here, for another 35 seconds total, and then that would turn red, and then the boulevard would be allowed to move freely with all their directions. So pass it off to Nick.
So we plan to sign and pave and make pavement markings according to MUTCD standards. 2 issues in particular that we want to address regard the northbound Bates portion, because the 4-lane approach can get kind of confusing. Basically, we want to add lane designation signs like something shown on the slide on an overhead structure after the Glenwood exit and before the curve in order to inform approaching cars of the lane assignments. Additionally, signs to accommodate trucks that move straight through the intersection will be placed. This is so because trucks going through may have trouble with the offset of the through right lane, so a sign telling through trucks to stay in the middle right lane will be needed. Basically, we're going to sign the approach as best we can to avoid a confusion at the intersection. ADA ramps will be added for all crosswalks according to ADA standards. These ramps allow the handicapped to cross more easily. For example, looking at the picture on the left, this is the Glenwood exit as it currently exists on Bates. It currently does not have an ADA ramp, so imagine someone in a wheelchair trying to cross that area. They would have to drop around 8 inches or so from the sidewalk and then cross, then somehow make it back up on the sidewalk. This is why we kind of want to put ADA ramps wherever they're needed, basically. Then this leads to the crosswalk that we want to add after the Glenwood exit. We want to provide a connection for the pedestrians that use the stairs that come down from Fraser Street in South Oakland. Those stairs will be integrated with the retaining wall to reach the road. Then there will be a 5-foot sidewalk to reach the Glenwood exit intersection. There, the crosswalk will be marked along with in-pavement lights and side strobe flashers to warn the drivers. We believe this is necessary due to the high traffic nature of the section of Bates, along with the increased safety that it would provide. Now I'm going to pass it off to Matt for the pavement design.
So for our pavement design, we had on the screen here, we have two guides that we use. On the right-hand side, the main criteria we use. It's the PennDOT Publication 242, which is PennDOT's pavement policy. And also, we cross-reference the AASHTO design of structural pavement structures also. So here's the pavement design process. So using the inputs from the geotechnical analysis, traffic, drainage, and flexible, we were able to determine the thickness layers of our pavement. And also for future consideration, we will be doing a life cycle cost analysis for future rehab. So just a couple key terms that for future reference in the presentation. So the monitor of resilience is just basically the measure of the stiffness of the subgrade. The average effective roadbed soil resilient modulus is the same thing as the resilient modulus, but it just takes effect the seasonal each season, and ESOLs, which is equivalent single axle load, which is an 18 kip single axle load with dual tires. So our first step is we need to find the soil classification of our subgrade. So on the right-hand side, we use a soil classification map from Arizona State University to determine that we have 4 layers of A4 soil, which is classified as in the AASHTO as fair soil and is silty soil. The 4 layers are 60 inches in depth, and all 4 layers combined have an average resilient modulus of 14,500. So for this part, to find the average effective roadbed soil modulus, one of the 2 major criteria is finding the length of seasons. With the length of seasons, if any of these months were like changed to something, it could really drastically change what our roadbed modulus will be. So using engineering judgment and the AASHTO guide, we determined that these criteria is for our months for our seasons. And the second criteria is finding the seasonal resilient modulus. So we made an assumption that our average resilient modulus, or our average resilient modulus that we found for our soil classification will be our summer period. And using the AASHTO guide and using our guides, we found that the other 3 seasons, relating the seasonal resilient moduluses, we found a cumulative relative damage for each of the seasons. And using the relative damages, we found the average effective roadbed soil resilient modulus to be 9,000 psi, which relates to our soil classification as it's not It's not the best, it's not the worst, it's basically fair. Okay, for our traffic analysis, using the ITMS database, we found the ADTT, the current ADTT for Bay Street, and we grew it to 1.6% to find that it was 1,904 trucks, and making the assumption of a directional factor and lane distribution, and using a 20-year pavement design period, we found the growth rate of easels as 18.68. And here's just a breakdown of the design easels per vehicle classification. When we did our traffic counts, we found the percentage of each of these classification of trucks, and we determined that the 2-axle 6-tire was the most frequent truck that was found, and we also found that the 4-axle single unit truck gave the most damage. Adding up all the easels, we found that our total design easels per year were 5 million. So for our drainage analysis, our base course was found. Our base course we use is asphalt treated permeable base course. PennDOT, this is a standard that PennDOT mostly uses for their base course because it has a high permeability, so it's a high infiltration rate. As you can see with the time to drain, that they're both less than 2 hours that you see in the chart in the table below. So the quality of drainage for this will be excellent for both cases. Our drainage pipe design, we found that the flow from the permeable base is roughly 28,000 cubic feet per day. So for our pipe design, we decided to go with a 5-inch under drain pipe that is corrugated, that has a flow of, it's not there, but it's a flow of about 46,000 cubic feet per day. And since normally for asphalt pavement, we locate the pipe underneath the shoulder of the roadway. Since we don't have a shoulder, we decided to put the pipe underneath the curb gutter. So we decided to go with a flexible pavement design for our option, and we needed to find the inputs for the structural number. The structural number is just the structural integrity of each pavement layer. And using the following criteria, we determined that, so we used PennDOT's standard pavement components of 9.5 millimeter wiring cores, 19 millimeter binding cores, 25 millimeter base cores, and we determined our base and subgrade. And we found that for our surface course, the values of the structural numbers were very low, so we made them negligible. And then for each of the other 2 layers in the subgrade, we found structural numbers to help us figure out our pavement thicknesses. So here's a table of the existing pavement structure of our roadway. It's found in the RMS data, PennDOT. So back in 2007 was the last time they resurfaced the roadway, and they milled it 3.5 inches and put a 1.5 inch binder course and a 1.5 inch wearing course and a 2 inch binding course. So using the layered analysis approach, using our structural numbers, we were able to determine our thicknesses on the right hand side for each of our layers. And our layers are color coded because on the next slide is basically our typical cross section of our pavement design. So each layer is corrugated to this. So the top is the red is the wearing course, and the purple is the subgrade, or not, it's the subbase. And then for future consideration for rehab, we did a life cycle cost analysis for the halfway point in our design, for our design year. Using the following criteria, we found a rehab cost of $285,000. So for our relocation of our utilities, so existing right now, utility poles are existing on both sides of the roadway. So once we widen the roadway, we're going to move the utility poles from the northbound side to the southbound side. So we're going to have all the utilities are going to be going on the southbound side. For the drainage existing, they're on both sides of the roadway, and they will stay on both sides of the roadway. And by the utility guide standards, we will determine that the poles will be 175 feet apart and the inlets will be 225 feet apart. And now I'll send it over to Amy to talk about the CM front.
So now that you know our design and what we want to do, I'm sure you're all wondering, well, how are we going to do this and what is it going to cost? So to start the schedule, the first part was to break it down into phases. I did this by creating a work breakdown structure, which is just a tool used to separate all the tasks and break them into activities to show how they all relate to one another. So our structure broke it down into 4 areas, which included a design pre-construction section and then 3 actual construction phases. The first phase for construction is demolition. The red area on each map shows where the phases will be happening. The main components of the demolition phase are clearing and grubbing, tree removal, and then demolishing the 4 existing buildings that will be on properties that we acquire. During this phase, traffic will continue to operate as normal, but delays are to be expected, especially for anyone using the Oakland exit from 376. Phase 2 is broken down into 2 subphases. The first is the construction of the northbound lanes. These would be the 2 new lanes. Other major activities in this phase include the excavation of the hillside and the installation of the design-build retaining wall. Phase 2B would be the southbound lane rehab. So in this, we will be rehabbing what is currently existing and be reconstructing the intersection at the Boulevard of the Allies. In this phase, the traffic will be shifted onto the new northbound lanes that we completed in the last phase. So this way, we really don't have to shut down the road for any extended periods of time. There would just be minor delays. The final phase can happen after all 4 lanes are reopened to traffic, with only minor shutdowns of 1 or 2 lanes. This phase includes the construction of the bike head path, landscaping, and all the lighting installations. And pictured in this cross-section is the final product after phase 3 is completed. So after we plan the phases, we could break everything down further into activities using the work breakdown structure. And this image is just a portion of our structure that shows all the activities that we then use to make the final schedule. To build the schedule, we used Oracle Primavera P6 software. So we took the activities from the work breakdown structure, we put them in the P6 software and gave everything an activity ID and a description of the work that's happening. After this, we applied appropriate calendars to each phase. For example, there would be a paving calendar because you can only pave at certain times of the year. There's a seating calendar, and then there's just a standard 8-hour day, 5-day-a-week calendar that includes holidays and expected weather delays. Once this was done, we could apply durations to each activity, and these are based on production rates and what the quantities of each activity involve. After this, the final task was to tie each activity together with relationships, so that really shows how the project would proceed from activity to activity. So after the setup, the project is automatically scheduled by the software. This is a list of the major milestones on the project and their completion dates. The project from final design to completion would take 1.5 years, and the actual construction phases would take 10 months from demolition to completion. To estimate the project, we could do this after the activities were done. We use the PennDOT's publication 287 unit pricing guide. It gives historical unit prices for similar projects that PennDOT has done. So we use PennDOT's activity ID numbers in each activity just for easy reference in case we wanted to go back and see where we were getting these numbers. Since we use the 2015 edition, we applied a 1.6% inflation rate, which that is the government rate that was set from 2015 to 2016 for inflation. If any items were not listed in the PUB 287, we actually went out to area contractors and requested quotes for these items. So after compiling all the unit prices and the quantity takeoffs for each item, we are able to form two separate estimates. The first estimate is the total project cost to the owner, PennDOT, and that is $24.1 million. The second estimate is what the owner can expect the project to go out to bid for to area contractors, and that is $18.3 million. So this shows the breakdown for the total cost to the owner. It includes all construction costs, design fees, land acquisition, and the utility relocation fees. And we just want to note that although $24 million might seem like a huge amount for this project, over time, it's going to be saving a lot of money in the long run when you consider time delays, emissions that are going into the environment from cars idling, and fuel consumption. This is the breakdown for the contractor bid sheet. This only includes the general conditions and all the items in the construction phases. So the general conditions for the project include various overhead costs such as the project offices on site, temporary utilities and permits, things of that nature. This bid item totals to $150,000. In order to complete this project, PennDOT will be required to acquire properties on the east side of Bates Street in order to make room for the widening. We use the Allegheny Assessment website to find out information about each property, such as the value of the property, who owns the property, and the total square footage of each parcel. This site also provided maps with the boundaries for each parcel, so then we were able to take that and overlay it on AutoCAD with our design, our roadway design, and it showed us exactly which properties would be affected by this plan. The total cost of land acquisition would be $865,000. We'd like to say thank you to all of our contacts who have worked with us throughout the semester, and a special thank you to all of our professors for their guidance and support. Thank you for coming. Are there any questions?